So once again, the bias is what we do on average minus the true value. So that can be positive if we're like sort of consistently overestimating. We always make a number that's too big, or most of the time we make a number that's too big, then the bias will be positive. If we're consistently underestimating, then it's negative. And I ask you to sort the bias at 45 degrees, 60 degrees, and 0 degrees from largest to smallest. Let's see what you said. Okay, submission counts. Okay, it's off to the side. All right, blank 1, this is the smallest value. So most people put bias when x equals 60. This is this one. So people think the bias at x equals 60 is the smallest. Then in the middle, pretty split between 45 and 60. And then the biggest one is when x equals 0. Let's start with this biggest one. Most people said the largest bias happens when x equals 0. We're talking like, these are in order with inequalities. So this is the largest and most positive. If some of the other ones are negative, they would be lower. And this is correct. So if you chose bias when x equals 0 is the biggest value, is the third blank here, then you got it right. Let's look at this situation and discuss why this is the case. So that was good. I want to turn off this thing and error. Where's the error? Error label. Okay, turn this off. Okay, so let's go to x equals 0. And this one has a large positive bias. Okay, in this situation, it looks like there were no points in this little slice over here, which is somewhat annoying. Oh, there's only 1 point. Okay, good. So the true value is 0. In the window of size 10, there was only 1 point, which was at -4 in this situation. So the estimate is -4, right? You average the 1 point, you get -4. However, as people, I think, at least half the class figured out, the bias here is actually somewhat positive. So even though here it looks like we're underestimating the true value is 0, we estimated -4, seems like we're underestimating. I claim that on average, we overestimate. Does anyone want to explain why they thought that was the case in their words? So you got it right. It is actually, this is sort of an outlier. Here, let's re-roll. Let's re-roll the dice. There's a button here to re-roll the dice. Where's the re-rolling the dice button? So generate data should be somewhere. Plot the data. Test point. Window slider. Error visualization. Generate data. Here we go. So this is the seed value that makes everything random again. So if I re-randomize it, every time I re-randomize it, actually I can make the computer re-randomize it. Okay, you'll see that it's bouncing around. So I'm having the computer animate re-rolling the dice and re-animating it every time. And you'll see that it's typically above 0. So sometimes it's below 0, but sometimes it's above 0. And on average, the average value of this estimate at 0 is above 0. It is above 0. So there's a positive bias here. We're on average overestimating. And there's sort of a simple kind of way to visualize or explain that. Does anyone want to say why they think it's an overestimate? It's true. If you chose that value, you got the answer right. Do you guys want to talk for a second? Okay, talk amongst yourselves for 1 minute, and then I'll come back and I'll ask you again. So why is it that the average here is an overestimate? On average, this is above 0 and not below 0. And remember how things are generated. The blue is the real true value, and the points are sort of at the blue curve plus or minus some random amount. So there's the blue curve plus some random wind. Why would it be that on average, the average of the points in this little purple window is above 0 and not below 0? Okay, I will set you free for 1 minute to think with your neighbors and come up with a nice explanation why, and then we'll come back together and we'll discuss as a class. And I can tell you why in my words as well. Okay.
Your estimation is points on the right end.
Okay, so you've had a minute to chat. Does anyone have a nice way they thought about it to see that the average value of the estimate here is above 0 rather than below 0? What was that?
So I was saying that I was guessing that it can come through them if we take out the mean for the estimated and the true value.
So you want to take out the, so that's, okay, this is exactly what when you're talking about the bias, you're talking about what the model does average over any universe where you get the data. So you see the purple points are jumping around. We have 30 data points.
Yes.
And our purple estimate is as I re-roll the 30 data points and re-randomize them, sometimes the estimate is above 0, sometimes it's below 0. The bias is asking, on average, are you above the blue line or below the blue line? On average, are you above the blue line or below the blue line? So that's what bias means. So indeed, we're trying to take out the randomness in some sense, right? But how things are constructed and what's going on is important to see how it is. So that is what you want to do. You want to take out the randomness and see what it does on average. And yeah, you can figure out actually there's a nice formula for what it does on average that you could even write down if you've taken a calculus class. But even if you don't know the formula, you can maybe see why it's positive. Does anyone else want to?
I have a question.
Yeah.
How exactly is that different from the variance?
How is that different than the variance? The variance is something like how much this thing is jumping around, right? So this purple point, it could jump around a lot and always be on average bigger, or it could jump around very little and be on average bigger. Here, let me give you an example. We said that if the window size is very big, then the variance is low. And you'll see what happens is, remember before it was jumping like up and down and up and down, and it was doing these big jumps. Sometimes it was like -5, sometimes it was +5. That was high variance. Now I've made the window size ginormous. It's very low variance, and you'll see that this thing is jumping, and it is kind of not moving very much. So the variance is sort of like how much this thing is moving, and the bias is where is it? Is it above or below the true value? You can think about this as like if you're really bad at darts. There's two ways you can be bad at darts. One way is you can be like all over the place, like you're hitting people in the room, you're like throwing it above, below, you're all over. Another way you can be bad at darts is you're very precise, but you are throwing it in the wrong spot. So you always throw the darts exactly over here on the light plug over there and like cause a short circuit, but the dartboard is over here and you get no points. There's two ways to be bad at darts. Just like there's sort of two ways to contribute to the error. You can either be consistently wrong and not move around a lot, or you can sort of be jump around a huge amount. So this one should jump around a lot more, but let me bring this back down to 10. So this one jumps around a lot more, but you can be either closer or further away from the true value, which is 0. So that's a great question. So we're looking for the average value, which is we're talking about bias. Okay. Any other ideas? Why should the bias here be positive? That's what we're trying to explain. Yeah.
I'm guessing. I don't know the answer, but maybe it's something related to all the irreducible error.
So the irreducible error is again the irreducible error is saying no matter how good you get it, it's still going to jump around some amount. So even if you set the window size to the perfect place, this thing is still going to jump around. You're not going to get a perfect answer. And in fact, yeah, let's start with what the blackboard was last time. So this was the very last thing we wrote down, is that the total error can be decomposed as a sum of 3 things. There's the irreducible error. This is like even if you are perfect, you will always have this error. There's the variance, which is somehow like how much you're jumping around. And that is the kind of thing that goes down with the data size. So if you make the data size bigger, you'll jump around more. And this is the last term that we're discussing now, which is the bias. And the bias squared is what goes into the error. The bias can be positive or negative. So you can either consistently overestimate or consistently underestimate. And either way, it gets squared, and that gets added to the total loss.
So,
Yeah?
can we use area under the curve?
Can we use the area under the curve?
Yes, if we
Ah.
can integrate through the area.
Yes. Okay. So the area under the curve. So okay, this is a good point. This is all of this is the loss at x. This is the loss at some point x. This is what I have written down, is the loss at some point x. So you tell me the x value, this is the total loss, right? And in particular, so we're doing the example right now of x equals 0. We're doing x equals 0. If you wanted to know the entire thing, then you would take the formula for 1x and you would integrate it over all x values. Okay, so this is the loss at some point x, and sometimes you'll talk about the total loss. Means average over all x values, and to average over all x values, you do an integral. So you do an integral, in our example, x equals 0 to 90, and 1 over 90, and then you do the loss at x dx. Okay, so this is the average value of the loss, and indeed that is a picture on the Desmos thing. There is this error visualization, which is how much you're under or overestimating. So the function you get from doing this thing is somewhere, function estimate, is this purple curve, right? And the purple curve is sometimes over and sometimes under. The error is exactly something like the square of the area. You know, when it's red, you're underestimating. When it's orange, you're overestimating. Let me stop it from moving around because it's driving me crazy. Okay. Okay, stop. Okay, pick this one. Okay, so when it's orange, you're overestimating. When it's red, you're underestimating. And how far off you are is that area. The loss is you take that difference and you square it, and you average it all up. So you do the sort of the area squared of this picture, and then you average over all the things, right? So that you take the average loss is what you get, again, when you start to make it random over and over again. So averaged over all these things, that will give you what we're talking about, the loss. Okay, so the question I'm asking now about the bias, it's got nothing to do with this error thing. We're just talking about just at one point. We're sort of understanding one point first, and then we'll understand more points. Okay, let's turn off this and this and this. Okay, turn off. Okay, great. These are all fantastic questions. I think we're hopefully starting to understand this thing a little bit better. Okay, let me make it a little bit bigger. Let me make the window bigger. I'll make it this big is the maximum bias. This is the biggest bias you can get. And right now, the estimates you can see are quite a bit larger than 0. Why are the estimates over here quite a bit larger than 0? That's saying we have a lot of positive bias. Why is that? How would you explain that to somebody?
Distance.
Go ahead.
The distance is more like whenever you shoot a cannon, it will travel a little bit of distance.
Yeah, right. So we're trying to estimate how far the cannon goes when we shoot 0 degrees.
Yeah.
But we're using all the points up to 0 to 45 degrees to estimate that, right? And of course, it goes further. The bigger the angle is up to 45 degrees, the further it goes, and that's quite a bit of an overestimate for what's happening at 0, right?
Yeah.
So in this situation, you have quite a bit of positive bias. You're overestimating consistently because you keep using angles where the true answer is larger than the value you're looking for. You're looking for a value of 0. That's the true answer you want. And you're saying, let me average points over here where the true answer is 10, and I'll average those up to get my answer. So of course you're going to overestimate, right? And you can see that it's overestimating. The average of all these points is quite a bit larger than this. Hopefully it's clear in this situation why the bias is positive. Now let's go back to the question that I asked you, which is when it was only 10. So a little bit harder to see, but it's the exact same idea, right? 0 is the minimum it could ever go, right? So if you average 0 to 10 degrees, those 10-degree shots are going to go further on average than the 0-degree shots. And by including them in your average, you're overestimating what is going on. So this is, again, positive bias. You're overestimating because you're including shots where the true value is larger than what you want.
What happens if we narrow down the window to like 1 degree?
Yeah, well, then it's still going to be positive, but very, very close to 0. So because 0 is the sort of absolute minimum of the true blue function, any window that includes the absolute minimum is going to include things that are larger. So at the absolute minimum, you will always have positive bias. You will always overestimate, no matter what you do. And that is unavoidable. The size of your bias, though, does scale with the window, right? If you have a big window like this is the maximum possible bias you could get. The minimum possible bias you could get, you can make this like really, really small, and then you have very close to 0 bias. Note that the bias starts to go down again if you include the whole thing. So it's the bias is maximum here, and now the bias is going back down, which is kind of weird. But it's because you're including points, again, that are closer to the true answer. This is sort of like an unexpected, weird coincidence for you. You made the window ginormous, and you started to get better bias. But it's only because you were doing really terribly over here. So, not much gain. Questions or comments about that idea? Let's write down, I can even write down a formula for the bias, for how big is the bias here. And if you've taken a good calculus class, you will see what's going on in this formula. Let's write that down. So, as an example, let's calculate the average value of, over the data, of f hat of 0. This is the bias. This will be part of the bias at 0. At x equals 0 for the cannonball problem. Okay, so at f hat of 0, I claim that the average is going to be the integral from 0 to 10, 1 over 10 of f of x dx. And what this represents is take the true value and take the average value of the true thing between x equals 0 and x equals 10. So if you look at the picture, what's going on is we're getting a point randomly between here, and that point, on average, it's not above the blue line or below the blue line. On average, it's exactly this blue line. So what are we estimating here? It's whatever the average of the blue function is in this little window. And that's the true function. That's f of x. So that's this formula. So this is the average. Or you can even write this plus 0 if you want. You say plus 0. So the noise on average is 0. And then what is left over is the true mean. And the true mean, we get anything between 0 and 10 because those are the points we're looking at. The true mean. Averaged. Okay. So that is the bias at 0. Actually, that isn't the bias at 0. To get the bias at 0, you have to subtract f of 0. And if you subtract f of 0, then you get the bias. In this case, f of 0 equals 0. So it's nice and simple. Whatever you do, that's the bias. Okay, so in this situation, this is positive. Positive. Okay. That one is positive. Questions or comments about this? All right. I'm going to send back the original warm-up question we did about the bias for the other 2 points. So at these two, x equals 45 or x equals 60, you guys were exactly split on which one is bigger. And bigger here means more positive. Okay? So I'm going to send this one back to you guys. You're going to re-vote. And this time, we're going to try to get a consensus where most of the class is on one answer or the other. Hopefully it's the right answer. Which has more positive bias, at x equals 45 or at x equals 60. I'll send it back to you guys. I'm going to open this one up again, and then we will take it from there. Do I have a button for that? Okay, so I'm going to duplicate this, take a couple minutes. Feel free to talk to your neighbors, and we'll take it from there. Bias sort V2. Okay. Okay, there's like 1 minute left. I want to take it up in 1 minute and see how you guys did. So put in, even if you're not 100% sure, put in what you think is going on. after 1 minute. Yeah. Oh, well, the bias isn't about the seed. The bias is about what happens on the seed. So looking at one particular seed doesn't tell you any information about the bias. You have to ask yourself what happens if I bring some teaching curve. Okay, yeah, there was a really great question over here, which was about when you're looking at the bias, is that the same kind of question? Let me freeze the seed over here. Let's freeze the seed. Generate data. Okay, seed. So one thing you can ask yourself, if you have a particular fixed seed, you can say, are we overestimating or underestimating, right? So you can put the function back on, and you can say, like, over here, the purple function is above the blue function, so that is an overestimate. And you can say, over here, the purple function is below the blue function, and that is an underestimate. And then you can say, okay, is that the same question as the bias? And the answer is they're related, but no, they're not the same. Over or underestimate for this particular seed is like what happened this time, and the bias is what happens on average. Is it on average an overestimate or an underestimate? So yeah, you could sort of mentally replace that with most of the time, and that's like close enough to correct, but very technically it's the average. So on average, is it an overestimate, or on average, is it an underestimate? That's the bias question. For one particular outcome, you will never, you don't know. You have to think about how is the data generated, and that will tell you the bias. Okay, so great comment over there. Let's see what people said in the Mathematize this time. Okay. People are still pretty split. So 10 to 8. 10 to 8. Okay, hopefully everybody got this one. Okay, that's good. People were listening for the first part. Okay. So I guess one of them is in the middle, and then one of them is the most negative one. One of them is the most negative one. And by a margin of 10 to 8, people think the most negative one is x equals 45. So x equals 45 is the most negative bias. But again, it's very close to 50-50. If it was 9 to 9, it would be exactly 50-50. We have 10 to 8. Does somebody from either camp, somebody who chose x equals 45 or somebody who chose x equals 60, want to explain to me why they think that is the most negative bias? Yeah.
So I chose x equal 45 because the estimated value is near to the true value, because the curve is dead, so bias will be less dead.
Okay, so you're saying, let me draw a little cartoon sort of with what I understood. So this is the true curve. Okay, we have this little purple zone. And then you said something about the curve of it and the true value. Say that again.
The estimated value is near to the true curve, like.
The estimated value is near the true curve. So let me draw the true value. I know how to draw. That's this one. This is f of 45. That is the true value. How did you think about where on this graph is the estimated value? What is that to you?
So the points are near the true value if we see in the graph. And estimated is average estimated value. So it will come near to the true value. But at the 60, it will be little upper side of the graph.
Okay. So at f. Okay. So this is f45. This is f60. Okay. And then here's the window for f60. Okay. Let me draw these as two separate pictures, so that we don't get confused. So this is f45. Let me draw it like that. It's like a little thing like that. What happens outside of the window doesn't matter to us. The only thing that matters is in the window. So this is f45, and f60 is something that looks kind of like this, like that. Okay, and f60 is here in the middle. Okay, and I think you're telling me something about how much is the graph changing around this window. And I think maybe you're saying something like this one is flatter than that one?
No, like value, the average value of the estimated in the second, it will be above side because the points are outside of the graph.
Okay. So you're looking at the average value of the blue curve, of blue. Blue is true.
Yes.
Okay, let's do the average value of the blue. One way you can do the average value is, it's got to be somewhere where the amount of stuff above it and the amount of stuff below it is evened out. So what's the average value of the blue curve in this little window? Let me take an eyeball at it. I think it is this kind of line, something like that, right? Where the amount of stuff above it and the amount of stuff below it is exactly evened out. That's the average value. So this is the average value. This is the average value. So in fact, that average value, that is exactly what we're looking for. If we pick a point at random, the points, because the noise will cancel out, the only thing that's left is the average value here. So this is exactly the expected value of the data of f hat of x, right? And you could also write it as an integral. It's the integral from 35 to 55, 1 over 20 of f of x dx. But it is this line, and it is just below the true value. And so the bias is exactly this difference, this minus this. It's some negative number, how far down you have to go to get to this thing. That's the bias. Okay, that's the bias over here. Let's do the other one over here. In this situation, what is the average value? Again, you got to draw a slice through it that kind of has equal amount of blue curve and equal amount of blue curve above and below. So where would it be? It's actually something like this. I think it's very slightly negative, but close to 0. In fact, if this was a perfect straight line, then it would be exactly in the middle, right? If it's a perfectly straight line, then the middle is exactly the right place. It's not perfectly straight because it's a little bit curved over here, but it's extremely close. And so in this situation, this is the expected value of f hat of x with respect to the data. And it's 1 over 20. You can do the integral from, I guess I said this was 60, so the integral from 50 to 70 of f of x dx, if you want to write it down as an integral. And here, there's parts of the window that are above and parts of the window that are below, and they sort of cancel out, right? Whereas below, in this picture, every single thing in the window was below the value we wanted, right? So every single data point is pulling down the true value that we want. Over here, some are pulling it up and some are pulling it down. Okay. So, yeah, okay. So which one is more negative? The answer is f of 45. X equals 45 is the more negative bias. Is the more negative bias. That is the answer. Okay, so 10 out of 18 people got it, which is pretty split. Maybe you got bamboozled by the pluses and minus signs. So there we go. These are the true answers. So pretty split. If somebody chose x equals 60, you shouldn't feel bad. You should ask me a question so that we can help clarify. Maybe it got clarified as we went. Yeah?
Yeah, it's like when it's x equals 45, wouldn't it be like more flat? So the difference would be smaller.
Yeah, so this is the thing. How flat it is doesn't matter. How curved it is matters. So, and that's because if it was a perfectly straight line, the bias would be 0 because they would have an equal amount of stuff pulling it up and down. Let's do a thought experiment. So this isn't in the picture, but what if it was like that? Then I claim the bias would be 0. So if it looked like this, I claim the bias would be 0 because the average value and the value in the middle are exactly the same. So if it's a perfectly straight line, then the bias is 0 for this kind of problem. So what matters is how much it curves. And it's curving sort of more at the very top than it is at the side. At the side, it's actually pretty close to a straight line. That's what's going on. And actually, maybe I'll say even more, you can show by doing a Taylor series expansion if you are a very mathy person. So this is equal to x minus delta to x plus delta over 2 delta of f of, okay, I shouldn't call it x. I guess I should call it u du. This is approximately delta squared times the second derivative of u. And this is in the videos. Yeah, and this comes by doing a Taylor series expansion to second order. Maybe there's like a 1 over 6 or something. Okay, I'm going to put a 1 over 6. So if you want to see this, you can go watch the video in detail or the notes. But so the thing that matters is how big is the second derivative of the function. So when the function is very like concave down, then you have a lot of negative bias. If it's very concave up, you have a lot of positive bias. If it's perfectly straight, then you have no bias. And this kind of thing is part of what is contributing to our trade-off. So the thing we actually care about is this total thing over here. And that is why you don't want to make the window too big. If you make the window too big, this bias increases like delta squared. So you make delta bigger and bigger, that bias term is going to swamp your error. So you don't want to make delta too big. It needs to be balanced with the variance. Yeah?
Yeah, but for 61, would it be like the second derivative become more greater as the degree goes higher? Because it's more and more sharp when the angles go higher.
Yeah, so it turns out the picture that is plotted is a sine graph. And a sine graph has the property that the second derivative is proportional to the original value. So the two derivatives of sine is against sine. One derivative of sine is cosine, another derivative of cosine is sine. So basically, how curvy it is proportional to how high it is. So the highest part is the most curvy, the middle part is the middle curvy, bottom part is straight, not
yeah,
curvy.
So I mean,
Yeah.
for 60, if you do the average, like
Yeah.
for the left, that would be a little bit higher, but for the right part, it would be a bit.
Exactly, yeah. So yeah, that's true for 60, like we said in the picture over here. Okay, can I move over? Let's try like this. Yeah. So the bias is negative and small at 60, and that's because it's curved down a little bit. So the second derivative is negative, but not as negative over here.
I see.
Yeah. Yeah.
So, in your opinion, 45 and 60, which one is more okay?
Which one is more concave?
Yes.
45 is more concave. More concave.
But don't you think it's from the perspective from which you look at it?
Well, I mean, I know the true function. So the true function is the sine function, and like you can calculate the second derivative, and it'll be more negative here than there, right? So, like in the actual example I gave you, there is a true answer that is not up to opinion. That is more concave over here. It is true if you're just looking at the picture, like you could maybe argue both ways. I tried to make the picture so that you could see that it was more negative over here because you're sort of getting pulled down from the left and the right, whereas over here there's a kind of a cancellation between the left and the right side, and so the amount you're getting pulled down is less. But it's true, like if I just give you a picture, you can never know for sure unless you start like measuring or something. So everything I said is true, and hopefully like you figured it out from the picture, but like without actually doing math, you'll never know for real. Yeah, this is a great point. Is there a question here as well?
Yeah, so I was just thinking that what we have here is the estimated average for all the body change we resample the data.
That's right. That's right. Mm-hmm.
Okay, so but if we had just looked at the first C that we did without us to change them.
Yeah. So this is the thing. What happens in a particular seed is kind of unrelated to the bias. The bias is what happens on average, and so any particular seed, maybe you got unlucky and like this is not related to what happens. So this is the concept of bias and variance are thinking about what would happen if you repeated the experiment many times. Any particular outcome will not tell you the bias and the variance. And what we're talking about when we're talking about the loss, like this formula for the loss at some point x, this is the loss on average. So we're saying if we were data scientists and we repeated these, we went to one data set and we did the same thing on the next data set and the next data set and the next data set, what would minimize this on average? Of course, maybe you make a bad decision and you get really lucky on one data set, but that's not what we want to do. It's a little bit like when we were rolling the dice, I said the best answer was 2.5, but then I rolled the dice and it came up 4. So you're like, oh, we should have said 4. Like, no, 4 is a bad answer, even though you would have done the best for that roll. You want to make the thing that's best on average. Yeah, this is a really good point to like get your brain around, because in data science, it's this tension of we're doing everything with respect to the average, but in real life you have one data set. You have one roll of the dice that you're looking at. So you kind of sometimes have to be in average mode, sometimes have to be in this particular thing mode. It's kind of tricky to do. Yeah, great question. Was there a question here as well? Okay. This is fantastic. Anybody else for this thing? Okay, so this is the bias and the variance. And what is the point of all this stuff is that when you make the bias small, you sometimes make the variance big, and vice versa. And so there is a trade-off. So in this particular problem, the bias, this was growing like delta squared. And the variance is like 1 over the number of data points. That's like 1 over delta. So this is approximately 1 over delta. So if delta is really big, then you have a lot of data points, and then this is small. And if delta is really small, then you have a small number of data points and you have a lot of variance. So what you get at the end of the day, your best value is some combination of 1 over delta and delta squared. Let's do a graph of 1 over delta and delta squared, just to give you a sense of that. This is the kind of thing, this is why they make you take calculus, so you can look at graphs like this and figure them out. So let me make some constants. Let's make c equal 2, and let's make d equal 3, and let's do the graph c over x plus x squared. So there we go. Okay, ignore the negative part. We're only talking about delta, which is positive. But so this is a combination. Let's plot these things on their own. C over x, and put in a d here, dx squared. Okay, so the bigger you make delta, the smaller you make the variance. That's like the purple curve, right? So the bigger the window you have, the more samples you have, lower variance. That's good for us. We're decreasing the error. The bias is the opposite, right? If you make a really small window, you're only including points that really are what you want, and then you have an extremely small bias. So the bias gets bigger the bigger you make the delta value. And the thing that we're minimizing is the sum of these two. That's the green curve. And so what I want you to notice here is that the green curve has a minimum not at delta very big, not at delta very small, but delta is just right in Goldilocks. And this was the secret third option that everyone got last time, so I think you guys figured out that you should have some intermediate value. Now we've sort of explained why by decomposing it into two parts that are opposing. Two opposing forces have this balance in the middle. In our particular problem, you can also see that by looking at the size of the error. So there is the error visualization, so that the size of the error averaged over everything, and that gives a total value at the end for the root mean squared error. So you pick some window size, looking at all the points, averaging over all the points. How far away is the purple curve from the blue curve? On average, it is 1.91 units away. And what do I mean by on average? I mean take the square distance, average it over all these points, and then take the square root of that. So that's called the root mean squared error. And you can see when you change the window size, you change this root mean squared error. So if it's really big, then the root mean squared error is big. So the root mean squared error here is 3. You're off by like 3 units on average. How far is the cannon going? You're typically off by 3 meters. And if you make the window size really small, then you're also doing quite bad. So here, my error is like 2.86, right? I'm kind of really overestimating in some parts and really underestimating in other parts. And our job is to make the root mean squared error as small as possible, right? We want to be able to estimate what the cannon is doing as accurately as we can. And the best possible answer is something in between. So here it goes, see, look, like it started big, going down, 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 1.2, 1.21, but then it's starting to get big again, right? So that's exactly like the curve, right? You don't want too big, you don't want too small. If you get it just right, you can get the minimum value. Okay. Okay, what's the minimum value? 1.21. That's the best we can do, 1.21. If you make it bigger, it's worse. If you make it smaller, it's also worse. This is the best we can do. And in the video and in the notes, I have this theory, like doing this Taylor series stuff, and I calculate that the theoretical optimum is 11.58. Right now we are at, what are we at? Where's my window size slider? Plot the data, unknown true function. Window slider, here we go. Okay, 14.5. So if you do it, in theory, it should be 11.5. We found the real minimum was at 14.5. The theory has a bunch of assumptions and things. And the number of neighbors in each thing on average is like 9. If you re-roll it, it'll be a slightly different answer. Let's do one re-roll for fun. Generate data. Let's move my favorite seed, 42. Okay. So again, the theory is 11.5. Let's figure out where is this thing minimum. 2.3, 2.1, 1.9, 1.4, 1.3, 1.1, 1.1, oh, 1.06. And that was at, again, a window size of like 14. So that's about the right thing. Okay. So this is an extremely important idea in data science, that you have to find this balance between sort of matching everything perfectly. That would be like having zero bias, and making, just averaging over everything, that would be like having zero variance, or as small a variance as you can. You need to find a balance between these two things. And this is called underfitting and overfitting. It's like commonly how people refer to it. If you're chasing all the points, so if you make the window size really small, then you're sort of chasing the points. So there's like one point up here, you're like, oh, let me go fit that point perfectly. You kind of chase after that point. This is called overfitting. You're matching the data too well, and by doing that, you have very low bias close to zero, but this is bad, right? You don't want to just do this. I think before people take a data science course, they think this is the best thing to do. So people sort of naturally tend to overfit, right? They say, I have some data, I need to fit the data as best as I possibly can. How do I do that? Zero bias, chase after the training points. But that's not what you want to do. I guess another thing you can do is you can underfit. This is a less common problem, but here's really underfit because it's almost flat. You're not chasing after the training points enough, right? You could be doing better. Yeah?
So if you have like a control experiment where you try to work basically for every random situation possible,
Yeah.
would it be better to overfit in that case because you know you can't control for the random?
Yeah, okay, this is a good point. Overfitting, the word overfitting always means too much chasing after the point. So when someone says they are overfitting, that means they did a bad job. It's true that if you have like more points, like if the number of data points is larger, then the optimal amount is different. So for example, when you increase the number of data points, here I think it was on the 30 points, the optimal window is like around 10 or 15. But if I had 100 points, then the optimal window would be like 5. So overfit always means too much like chasing after the points, and the optimal amount will depend on the specific situation. But it's important that you don't overfit, and you will be accused by other data scientists. So they'll say, you are overfitting here, and what they mean is go less, right? This is a good point. Yeah, so overfitting and underfitting sort of refer to the direction away from the optimal value. Excellent question. Anyone else? Yeah?
So instead of calculating by theory, if we plot the graph of the mean square error, so we can easily find that where the graph is minimum.
Yes, okay, and in fact this is the next thing we're going to do, because this was all done in Desmos. Desmos is very nice for visualizations and sliders and stuff, but you can't do everything in Desmos. And what we're actually going to do is we're going to do the same kind of stuff, same problem, we're going to look at it in Python, and we're going to generate the same kind of thing. So, and I think the graph you're asking about is this graph. Let me zoom out appropriately. Okay, so this is the graph you wanted. So in Desmos, I was just sliding it around and I was looking at the number go up and down. That's the best thing you can do in Desmos. In Python in a minute, I'll show you how to do everything that was done in Desmos in Python. Ignore the red curve for now. We were working on the green curve, which is the nearby neighbor weighted average. So counting everybody within the window, that was our delta value on the x-axis. And the RMSE is on the y-axis. And you can see it's exactly doing this U-shape, right, where if delta is too small, you have a lot of error. If delta is too big, you have a lot of error. But if delta is just right, you have the minimum possible error. There's two other things that are plotted on here. There's this blue dotted line, which says the minimum possible RMSE. That is the irreducible error. So no matter what you do, you will never, ever get below this. And you can see that there's a little bit of a gap between what you can get and the minimum possible, and that's because you only had 30 data points. So as the number of data points goes to infinity, as you get more and more data, these curves will kind of slink down, so they will get down to this thing. But you can never beat that, even if you know everything. And that's the best you can do with what you have in this technique. Okay, there's another line over here, the dotted line over here. This is the RMSE of a constant estimator. So if you are forced to say, I always think the cannon goes 20 meters, that's the amount of error you'll get. So this sort of gives you an idea of the scale of what we're talking about here. This is like just average everything. This is like you're perfect. That's where we are. And you can see that it's critical you get the value right, otherwise you're leaving a lot of performance on the table. Okay. All right, great question. Yeah, and I'll show you guys how to do this in a few minutes. Any other questions about this cannonball example? Yeah.
So I have another curious question, like will the underfitting will be very bad on the testing or the overfitting will be bad?
Okay, this is great. So far, you said this word testing. We haven't done any testing at all yet. So what have we done so far? We have training data, which was the dots, and we have the truth, which is the blue curve. Okay? You're asking about something else, the testing, and there is a question that is related to this. Let me let me get that question going. Where did the mouse go? The mouse is lost. So let's do, yeah, okay. Let me do this. Fill in the blank. For a real life problem, we cannot calculate the RMSE of the model because we don't know blank. We don't know blank. So everything we've done so far in real life doesn't really work. And there is an important reason you must understand why. So I will let you guys fill it in. Take a minute and think. Okay. Put in your guess. I'll give you like 30 more seconds if you haven't gotten it in yet. But I want to get people's quick opinion on what is the thing. Everything we've done so far doesn't work in real life. All right. Okay. I guess I have to put a timer. People don't take it seriously. 15 more seconds. And then I will take it up whether or not you've put in your answer. Okay, so what is the thing that is missing in real life? Here's the thing. Okay, here's a little word cloud. The value, something. Okay, let's see what were the actual responses. Let's go one by one. The bias. It's true you don't know the bias. The bias is related to the thing that's supposed to go in the blank. So your bias is half right. The estimated value. You do know the estimated value. You construct the estimate, you do know the estimate. The test value, that will also be something that you will know. So none of these are right so far. All the data, you do know the data. This is good. The accuracy of the data, I want to avoid the word accuracy for now. Let's not use the word accuracy because that has a special meaning. That's like if you want to get it right or wrong, that's not what we're talking about. We're talking about get as close as you can. So this one is not quite right either. I don't know. This is a great answer because now I know you don't know. Okay, the correct value or the true value. This is the thing that you do not know in real life. So if you said something like correct or true value, true curve, the real mean, these are great. The Turu function, 0 points. No, that's very good. True value, truth. Yeah, this is great. All of these are perfectly right. So in everything we've done here, in the cannonball problem, it's all about the whole thing was worshiping the blue curve, right? How close can we get to the blue curve? And the blue curve was the truth, and we said, how close are you to the truth? And then we did all this, variance, bias, window sizes. All of it was how close is our estimate, the purple curve, to the true curve, which is the blue curve. But of course, in real life, you don't know the blue curve. If you knew the blue curve, you wouldn't waste your time with all this stuff, right? You would just be like, I know the answer, that's it, I'm done. In fact, the blue curve comes from physics. So if you take like a physics class, you can calculate how far a cannon goes when you shoot it. That's what the blue curve is. But in real life, you do not know the true function. So here it's called the true function. I use the word unknown because in real life, you don't know. So in real life, you have just the data and just this. And if you don't know the blue curve, you cannot calculate the root mean squared error. The root mean squared error was how far is the purple curve from the blue curve. If you don't know the blue curve, you cannot calculate this error. Okay? So this is a very important life lesson, is that in data science, you want to get as close to the true value as you can, and you have these thoughts about variance and bias and trading them off to get as close as you can to the true thing. But in real life, you don't know the true thing, and you don't know how close you are to the true thing. And you need to have a workaround, a different set of strategies to get around this fact that we don't know the blue curve, so we can't possibly optimize things. And this is a big deal. Big deal TM, okay? So what we're gonna talk about now is how you can get around this fact. What do you do if you don't know the true value? So up until now has been like nice theory to understand the problem, but it all involved the true value, and now we're gonna replace knowing the true value with something else. Before I tell you what the thing is that we're gonna replace it with, which was also the subject of the videos due today, so you probably already know, I do wanna start out with one really common thing. A really common mistake that people make, and I'll do that in a second, but first let me do some questions.
Validation.
Yes, it's going to be validation, that's right, yes. But before we do validation, I wanna do this thing. The error streams to be okay. This is great. Okay. This is a really common situation. A student is working on the cannonball problem and says, I made a graph of the error versus the size of the window. And it seems like the error is getting smaller and smaller and smaller the smaller the window is. I do not see this U-shaped trade-off curve that you are talking about. And here is the graph that they made. And in fact, the graph is also in the thing, in here. So I made the graph, and it has this U-shape. Very nice. That was the thing I just explained. But below it is this very similar code, almost exactly the same, with one super teeny tiny thing. Like you could spend an hour looking at this to find the small difference. There's only one difference. And now the curve looks like this. Okay, and again, you can ignore the red curve. You can only look at, if you want to understand this is the green curve, that's exactly the example we did in class. The red is like a slightly nicer version of the green, but they're almost exactly the same. And in this situation, the delta value, how big is the window, seems to be always shrinking. And it seems like you make it smaller, you get less error. And they're doing everything correct except one thing. So they're calculating the error correctly, delta is correct, the model is correct, and they're sort of seeing the phenomenon that smaller delta is always better. Make delta as small as you can, make the window as small as you can. And everything they've said is correct, even this word. The sentence is all correct, except for there's one misunderstanding that they have made. And it's such a common misunderstanding, I think it is absolutely crucial that you are able to look at this and go, aha, they made the big mistake that everybody makes. Okay, so now I'm gonna let you think for a few minutes and think of what is the mistake that they made, all right? And it's very much related to the thing that we're gonna talk about now about validation coming up. But what is the mistake that they made? There is one word that would fix everything and fix the misunderstanding. I will let you think about it. Okay, so take a few minutes, chat with your neighbors, and then I will tell you the answer. But this way, you will remember it better.
What did he do wrong? What did he do wrong? Sure, we can camera talks like that
this, but it starts from the lower. Yeah,
no, 0 marks. He does not know the truth.
Okay, there's only like 30 seconds left, so maybe you haven't fully figured it out, but I want to see your guesses. So put in any old idea you have. What is the student doing wrong? Any guess is fine. IDK also fine if that's how you feel. But making a guess is more exciting. So if you have any sort of guess, put that in, and then we will discuss what is going on. Okay, put in your answers. Okay, 10 more seconds to scare people with the small numbers. Okay. Okay, here we go. I'm doing it. I'm pressing the button. Okay, I don't know. Okay, great. I don't know. Fantastic answer. Okay, sum of weight without square. These things are kind of saying, oh, you calculated the root mean squared error wrong. That is a mistake people make, but that is not the mistake made here. So the root mean squared error is calculated correctly. Okay, not shuffling the data. Okay, there's some people have the right idea here, which is same data set. That's kind of the right idea. Not shuffling the data. I saw one that said like train something, test something. Overfitting without square. Okay. Same data set. Yeah, okay. These are the right idea. So this is the error. This is an error, but it is not the error that we want. And this is the mistake that people make. When you say the word error, you are not being specific enough on what you mean. So when the student said, I made a graph of the error, you should interrupt the student. Don't let them finish the sentence and say, what error are you talking about? Because there is more than one type of error. And you might say, well, so far, I haven't seen more than one type of error. What do you mean? And that's because when you know the true answer, we have been talking, the thing we've been discussing this whole time is the true error. The true error. This is all the true error. Let's put that in big orange letters. This is the true error. Okay? This is very important. Everything we've been doing so far has been all about the true error. What is the difference between the estimate we came up with and the true value f, right? But we just said, in real life, you do not know the true value f, and you do not know the true error. So when somebody says something like this to you, so first of all, in a real life problem, if somebody says the error, they're definitely not talking about the true error because you don't know the true error in real life, okay? So maybe it's like a toy problem and they're playing around, but in, quote, real life, you never know the true error. So if somebody graphs something like this, you can be sure they're never going to come up with the curve that I said, because my curve was the true error. Did I write true error somewhere? Well, okay, maybe I didn't. It'd be on some other one. So this is the true error. This is like when you cheat and you know the real life answer, this is what you get. And what the student did is they did something called the training error. So what they actually did is they have done this whole situation. They made a graph of the training error versus the size of the window. That is what their graph is, and this is an extremely common thing. So they forgot to tell me that it was the training error, and then they graphed the training error, expecting the training error to have this U-shaped trade-off curve, and the training error does not. What is the training error? It is this idea of validating what is going on by doing a train test split. So this is data validation, and this is the videos you watched for today, data validation. It is a very simple idea, and it even came up in our first class, which is use a held out test set. Held out test set in order to approximate the true error. Okay, so once again, you never know the true error, and the data validation approach says, even though we don't know the true error, what we can do is we can set aside a piece of our data set. That's what held out means. Set it aside. Don't use it in our sampling, in our methods. That's going to be called the test set. So the test set is what we hold out to train on, what we hold out to test on. So data saved to test on. Okay. And by contrast, everything that is left over is called the training set. The training set. And this is data we use to construct our estimates. Okay, and I'll add one more thing to this list, which is the truth. And in real life, you don't have the truth, the real answer. Okay, so in real life, you don't have the truth. In a lot of our practice problems, as we're learning, we do have the truth, so we can see what's going on. And so far, everything we've done up until now, I've only had a training set and the truth, right? And the training set was all the data points we had. The truth was that blue curve, and we were trying to use the training set to get as close to the truth as we can. But in real life, you don't have the truth, so you better learn a method that doesn't involve the truth. And so what we do is this test set method, where we split aside some of the data, and we split it into a training set and a test set. The training set is exactly what we do before. We have the points, we can do all those averages, but now we have this test set, and we use the test set as an approximation for the truth. All right, let me show you what this looks like in the Python code. So, okay, so here's the Python code. The next section is on these things. So how to choose delta in practice using a test set. And so here's the picture of what is going on. Is originally I had a bunch of points, right? This is the cannonball problem with no truth. And I have split the points into two groups. Some of them I've left as black dots. Those are called training data. And some of them are green X's. And those are called the test set, or train data or test data. So you can imagine I take all my cannonball shots and I just randomly choose some of them to be test and some of them to be train. Sometimes people will split it by 80% training, 20% testing. There's lots of different ways you can do it. And now when I compute my averages, okay, let me go to the, is there a nearest neighbor one? So I don't have to explain what this Gauss is, or did I only do Gauss? Okay, I only did Gauss. Let me quickly explain what this Gauss thing is. You can see what it is. Let's go. Is there one more we did? Okay, so this is what we've done so far in the Desmos, the nearest neighbor, and you can see it's very jagged, right? It has these like vertical peaks. That is when there's only like 1 point in your data set. You're doing the average of 1 point, and you get these like weird jagged lines. You can do exactly the same thing, but you can smooth it out a little bit. So instead of doing up and down and up and down, that's the nearby neighbor estimate. That's exactly what we were doing before. You can do the exact same thing with a Gaussian weight. And it's almost exactly the same, but it's smoother. So look, here, even though it's up and down, they're not as jagged. And that's slightly better than the Gaussian, or than the nearby weights. But otherwise, it's exactly the same. So here it is with a window of size 1, you still get something that is not perfectly vertical. It's a little smoother to work with. It's a little bit better. Maybe I'll make an extra video or something explaining the details, but you can just pretend in your mind that this Gaussian weight thing is exactly the same as what we were doing before. It's very slightly different, and all it does is it smooths things out a bit. It's a little nicer to work with. Okay, why am I telling you this? Well, the reason is I want to talk about what happens when you have a test set. So when you have a test set, so there's no blue curve here telling us the truth anymore, and when you compute the estimate is only made using the training data. So only the black points contribute to making this red curve. And then you can compute, just based on how far away are the green checks away from our estimate, you can get an RMSE sub-test. So this is the test error. Let's write down the formula for the test error. So the true error, remember, the true error is the expected value over the data of f hat of x minus y squared. So this is the data is x comma y. So here capital X and capital Y are random variables. They're generated according to some unknown process. And the error, technically the square error, is the difference between our estimate and the true value squared. And what is the test error? The test error. It's the same kind of thing, but instead of doing the true average, we're summing over our test data set. So it's the number of test points, and then you sum from I equals 1 to the number of test points. You do f hat of xi minus yi squared. So the true error is this data, we don't know what it is. You can never get that in real life. And the test error is just sum up kind of do an approximation of this by summing up over our test set. And you hope that the test set is kind of close enough to the data that these two things are close together. Okay, and in the picture that I drew over here, it really is, you take your meter stick and you measure the vertical difference between the green check and the red, and you see how far that is, and you square it. And you can do this for different values of sigma. So here is a sigma that is too wide. Sigma is the same as delta, how the width. Here's one that's a little bit better. Here's one. This is a great example where you can see that the curve is getting pulled up towards this black dot over here, right? This black dot, this training point is pulling up our whole estimate. We think the whole estimate is going up there. When actually the truth is like somewhere down here, and we're getting kind of a bad score, say on this x, which is part of life. Okay. All right. So, and here's one that's like way too, this is like, clearly this is an overfit model. We are chasing the training points too much. That's overfitting. And you can see that we're getting a lot of error over here because this black dot is pulling up the whole red curve, and we're getting a lot of error on these green checks in our test data. Okay, and you can do this for many different values. Because we're in Python, you can say, please run this over all the values, and then graph the error. And here is a graph that has the test error and the true error labeled. The true error, remember, we can never know that in real life. That is what we did at the beginning of the class. If you knew it in real life, that's what it looks like. And here's what the test error looks like, varying the size of the window. And what is the point of this? Is that even though I will never ever know the true error, I can do my best to make choices by using the test error instead. So for example, if I want to minimize, I want to find what value of the window should I use to make the window not too big and not too small, I can minimize the test error. And I would say, please make the window about size 17, right? Somewhere over here. The real answer is probably best around 12. So it's not perfect, right? The test set is some approximation of the true. But it's pretty close. Like, I'm not going to make it way too big or way too small. Okay. So this is the idea of a test set. We're going to come back to this idea a whole bunch of times. This is like the holy grail of data science. To me, this is what makes data science and not statistics. If you have a test set, you're doing like data science or machine learning or something. In statistics, you try to figure out how big the error is using other means, like using theory. Of course, they're related, so other people will disagree with me. All right, that's the idea of a test set. Any questions or comments about the test set? Let me leave you with one question, which was answered in the videos. So if you watch the videos carefully, you will know. Let's pretend I'm trying to do this cannonball problem. So I'm working on this cannonball problem. I want to find the best possible estimate. Like, my job is really to find the best possible estimate for how far the cannon will shoot for any given angle. Okay, I do this train test split. I split it up into an 80% training set and a 20% test set. Then I draw this graph over here, and I find the best possible window size is size 17. And then there's one more important step I have to do before I report the final answer to my boss, okay? Before the CEO of Netflix, before I report my answer to them. And that is this overlooked last step. And I will let you put in what you think this overlooked last step is. Maybe you remember from the videos, maybe you don't. Put in your guess now if you can remember what is the important last step, and we'll take this one up next class when we start on Monday. Okay, it's 12:50. I'm going to stop here, so put in your thing and then you can go. I'll be around for a few minutes. If you want to ask questions, feel free to come up.